titration curve that would result from titrating 1 molar hydrofluoric acid, really dangerous, with 1 molar sodium hydroxide. So the points that we need, we're going to need the initial point. I'm just throwing in that we're going to plot what it would be somewhere in the titration. On your homework it said 5 milliliters for all of these problems. 5 milliliters will be kind of a silly one for this one. I'd say more like 10, 20, 30 would be more interesting. The midpoint and the equivalence point. So the initial, this is before we've added any sodium hydroxide. So initially all we have is 1 molar hydrofluoric acid. It's a weak acid, we put it in water and we know it dissociates into fluoride and some hydronium. So we're going to set up an ICE table. It's 1 molar, we don't care about the water. We know some of it's going to dissociate. Whatever dissociates ends up as fluoride and as hydronium. So we have our ICE table and we know that Ka, since this is an acid, it would be given to us 7.2 times 10 to the negative 4th. It's going to be equal to our products over our reactants. So x squared over 1 minus x. So this is the part I like the most. I get to say that since this is at least 100 times larger than the Ka, this x will be so small that 1 minus x is pretty much x. So I'm going to multiply both sides by 1. It's the same thing. I'm going to square root both sides to get the x. So x, which is my hydronium, is going to be equal to, let's see, I have 0.0268. I know pH is the negative log of my concentration of H, so I'll negative log this, and I'll find out that the pH is equal to 1.57. So that's the pH of this 1 molar solution before we've started our titration, before we've added any sodium hydroxide. So the pH is 1.57. We've added 0 milliliters of sodium hydroxide. So the next thing we're going to do is we'll see what happens when we've added 5 milliliters. So 5 milliliters of strong base into this titration. So at this point, I know I have hydrofluoric acid, the weak acid, and I'm adding hydroxide. It's going to react 100% to make the fluoride, again, because this H is going to come off, go right there. So I'll have some fluoride and I'm going to have water. So since this is strong, it's going to react 100% and it'll go to the final. So I'll make an ICF table, meaning I'm going to use moles. I have 100 milliliters, or 0.1 liters, of hydrofluoric acid. For every 1 liter, there's 1 mole. So I have 0.1 moles of the hydrofluoric acid. For the base, I'm saying that I'm adding 5 milliliters. So 5 divided by 1,000, I have 0.005 liters of the sodium hydroxide. And for every 1 liter, again, there's 1 mole. So I have 0.005 moles of that strong base, 0.005. I know it's going to react until I run out of one of my reactants, so that'll be the 0.005 of the base. Once that's gone, it'll stop reacting. So I'm going to end up turning 0.005 of those moles into fluoride, 0.005. So at this point I say, what do I have that affects pH? I've got this weak acid, I have this weak base, so I know I have a buffer. And the equation for buffers is that pH equals pKa plus log of the base over the acid. Okay, so pH is going to be negative log of the Ka. So negative log 7.2 times 10 to the negative 4th plus log of the base, which is the fluoride ion, 0.005 over the hydrofluoric acid. And when I plug that in, I got, let's see, 1.86. So it's not really much of a buffer. There's very, very, very little conjugate base. It's pretty much still just a weak acid. It's barely a buffer. So pH is 1.86, and that was after we had added 5 milliliters of sodium hydroxide. So the next part that we're going to look at is going to be the midpoint. Okay, so midpoint is when you've neutralized half of your hydrofluoric acid. So we just saw in the last problem, we're adding sodium hydroxide. to make fluoride and water, and we saw that we had 0.1 moles of the hydrofluoric acid. So to neutralize half of that, we're going to need 0.05 moles of base. Okay. So what that's going to do is we'll use up half of this. This will all get used up. And we're going to end up making 0.05 moles of the fluoride. Okay, so we've got this, we have this buffer, and we know it's a buffer because we have hydrofluoric acid and its conjugate fluoride. So for buffers, pH equals pKa plus log of the base over the acid. And this is that special condition where we're at the midpoint, and at the midpoint, pH just equals pKa, because this log right here is going to be 0.05 over 0.05. So that's log of 1. Log of 1 is 0. So pH just equals pKa at the midpoint. And in this case, that's going to be the negative log of the Ka, 7.2 times 10 to the negative fourth. I think it was 3.14. So 3.14 is our pH. So I can put that in as my pH at the midpoint, 3.14. But I still need to know the volume. So how much sodium hydroxide did I add to get to this point? I don't know, but I added 0.05 moles of sodium hydroxide. I can use molarity to relate the moles and the liters. It was 1 molar, so this will be easy for us. We've got 1 mole for every 1 liter. Okay, so it was 0.05 liters of base was added, and that's 50 milliliters. Okay, so at 50 milliliters, you're at your midpoint, which is nice, and the pH is that. So in the next part, we wanted to know the pH at the equivalence point. Well, the midpoint's when you've neutralized half of the weak acid. The equivalence point is when you've neutralized all of the weak acid. So I can just say the equivalence point is going to be twice as far down the line as the midpoint was. So the equivalence point is 100 milliliters. And let's find out what the pH is there. So at this point, I've got this weak acid, and I've been adding the sodium hydroxide to it. And at the equivalence point, I'm going to neutralize all of my weak acid. So 1 to 1, right? So minus 0.1, minus 0.1. I'm going to be making this conjugate weak base. So I'm just going to be making some fluoride ion. And I can see, in the end, the only thing that I have that affects pH is this weak base. So unfortunately, I just did the ICF table. I had to because I had something strong. It was going to react to the final. I now have something weak, so now I have to set up a second table. This one's going to be ICE, though it's equilibrium because this is weak. So I take my weak base, I put it in water, and I know it's going to make the conjugate weak acid. There it is again, seems redundant, but it's the only way to find out how much concentration or how much H plus is going to be left in this solution. So I've got 0.1. I know I'm going to lose some, and whatever I lose turns into the conjugate. So from here, I know since this is a weak base, I can say Kb, it's the equilibrium expression of bases, is equal to the x squared over 0.1 minus x. I need to find out what the Kb is. I know Ka times Kb equals Kw. And I know that Kw is 1 times 10 to the negative 14th. It always is. It's a constant. It's on your Gregor sheet. And Ka was the K for that guy, so that's 7.2 times 10 to the negative 4th. So when I do Kw divided by Ka to get Kb, it ends up being 1.388 times 10 to the negative 11th. Okay, so that's going to be what this is equal to. 1.388 times 10 to the negative 11. And I can see that this is a really small number. X is going to be really small. So 0.1 minus something really small, I'm allowed to say is really just 0.1. I'm going to multiply both sides by 0.1, square root both sides to just get the x. And I find out that the x is equal to, I think I have 2.6 times 10 to the negative 6. I think that's what I have, but it got copied. It cut off my paper. So actually, I'm just going to do that one. So I have 1.388 times 10 to the negative 11th. I'm going to multiply both sides by 0.1. And then I'm going to square root both sides. And I have 1.7 to the negative 6. So I'm just going to check it one more time. Oh, you know what I didn't do? That was bad. That was very bad. There's something I did. This is an ICE table. With ICE, we have to use molarity, and I didn't. I used moles. But we can fix that really quickly, and we'll fix the whole thing. So the moles were 0.1 moles. The liters were, well, we're at an equivalence point. There's 100 milliliters of the sodium hydroxide. There's 100 milliliters of the weak acid that we had. So it's going to be 0.1 moles over 0.2 liters. This is really it's going to be 1/2 because I got 0.1 over 0.2. So this is really 0.5. So this is 0.5. And so this right here is 0.5. And then let me check it again. And it probably will be what I wanted. So 1.388 times 10 to the negative 11 times 0.5, and then I'm just going to square root. Yep, 2.63 to the negative 6. So, okay, good, we found a mistake. So then, I've got X, and X was the concentration of hydroxide. So if I negative log that, I'm going to get the POH. And for this problem, I have that the POH is 5.58. So that means, 5.58 something. So I have my pH is going to be 8.482. Okay, so 8.42. So that's my pH at equivalence point. So now I have all the points that I need. I can plot this titration curve. So let's see what it looks like. So I'm going to plot pH versus milliliters of sodium hydroxide added. Initially, the pH is 1.57. After I've added 5 milliliters, I'm going to call this 50 and this 100. After 5 milliliters, the pH is 1.86. We'll call this 7. After 50 milliliters, the pH is 3.14, so maybe just a little less than half. And after 100 milliliters, oops, I should put that over the 50 then. After 50, it was 3.14. And then at 100, that's our equivalence point. pH is going to be 8.42. Remember, this is the part in your graph where it just changes drastically. So I've got this quick change at first, and then a real slow up. Hit the equivalence point, go straight up, and then level out again. So that's our titration curve. Here's the equivalence point, here's the midpoint, and that's your initial, that was your 5 milliliters. Yay!